Module 8, Section 10.6, Polar Equations and Graphs. In the polar coordinate system, it's based on a point called the pole and a ray called the polar axis, usually drawn in the direction of the positive x-axis, as we see here. In this graph, we see our pole is at the origin, the polar axis is equal to the positive x-axis, our point P has rectangular coordinates x, y. It can also be located by giving the directed angle theta from the positive x-axis to the vector OP and the directed distance r from the pole to point P. The ordered pair P, r, theta gives the polar coordinates of point P. If r is greater than 0, as we see here, point P lies on the terminal side of theta, right here. And if r is less than 0, as we see in quadrant 3 here, point P lies on the ray pointing in the opposite direction of the terminal side of theta, a distance, absolute value of r, from the origin. If a point has rectangular coordinates x, y, and polar coordinates r, theta, then these coordinates are related as follows. X equals r cosine of theta, y equals r sine of theta, r squared equals x squared plus y squared, or r equals the square root of x squared plus y squared. And the tangent of theta equals y over x, where x is not 0. Let's look at plotting points with polar coordinates. In this example, we want to plot each point by hand in the polar coordinate system, then determine the rectangular coordinates of each point. For this point, r equals 2 and theta equals 30 degrees, so the point P is located 2 units from the origin in the positive direction on a ray making a 30-degree angle with the polar axis, which is our positive x-axis. So let's convert to the rectangular coordinates. We know that x is equal to r cosine of theta and y is equal to r sine of theta. So we have that x is equal to 2 cosine of 30 degrees, or 2 times the square root of 3 over 2. So we get that x is equal to the square root of 3. Then y is equal to 2 sine of 30 degrees, or y equals 2 times 1/2. So y will be 1. So we get the ordered pair square root of 3, 1. For this point, r is negative 4 and theta is 2 pi over 3. Since r is negative 4, q is 4 units in the negative direction from the pole on an extension of the 2 pi over 3 ray. So our normal ray, 2 pi over 3, is in quadrant 2. And if r had been positive, we would have been 4 units up. But since r is negative, we kind of flip over to the opposite side, or quadrant 4, of our ray 2 pi over 3. So let's find our rectangular coordinates. So x will be negative 4 times the cosine of 2 pi over 3, which is negative 1/2. So we'll get that x is equal to positive 2, and y, which is our sine of theta, is negative 4 times the sine of 2 pi over 3, which is the square root of 3 over 2. So we end up with the value of y of negative 2 square root of 3. So our ordered pair is 2 and negative 2 square root of 3. This next point, r, we have that r is 5 and theta is negative pi over 4. Since theta is negative, the angle is measured in the clockwise direction, and we'll have 5 units on our ray. So let's find our rectangular coordinates. So x will be equal to 5 times the square root of 2 over 2, or x is equal to 5 square root of 2 over 2. And y will be equal to 5 times negative square root of 2 over 2, or y is equal to negative 5 square root of 2 over 2. So our ordered pair is 5 square root of 2 over 2 and negative 5 square root of 2 over 2. A given point in the plane can have only one pair of rectangular coordinates, but it can have an infinite number of pairs of polar coordinates. 2 30 degrees locates the same point as 2 390 degrees. All we do is add 360 degrees to find a coterminal angle to 30 degrees. It's also the same point as 2 negative 330 degrees. We simply take 30 degrees and subtract 360 to find another coterminal angle that's negative. Or negative 2 210 degrees. And now I want to kind of demonstrate that. We see if we divide into thirds, we have 30 degrees here, 60 degrees, and 90 degrees. Whereas if we divide into thirds here, we're at 180, 210, 240, and then 270 degrees. So our point 2, 30 degrees is right here. If we look at negative 2, 210 degrees, notice that 210 degrees is in quadrant 3, and so we would look here. But since it's a negative 2, we kind of reflect across to the opposite quadrant, which is quadrant 1, which is our 30 degree line, and go 2 on that line. So it's the identical point. In this example, we want to give 3 other pairs of polar coordinates for the point P 3 140 degrees. So here we see our point is plotted. 140 degrees is in quadrant 2. If we take 140 degrees and we add 360 degrees, we'll get 500 degrees. So that would be the point 3 500 degrees, which is identical. If we take 140 degrees and subtract 360, we'll get negative 220 degrees. So that would be the same thing, except we'd have our negative coterminal angle. And then the other 2 angles that we see result from taking 140 degrees and adding or subtracting 180 degrees. Now, by doing only half with 140, we end up in quadrant 4. But since we're in quadrant 4, instead of using positive 3 to get our value of P, we'll use negative 3 for each of these, so that we kind of convert over back to the point in quadrant 2 that we want. And our values here would be 320 degrees and negative 40 degrees. So we've actually found 4 points instead of 3. Now let's determine 2 pairs of polar coordinates for the point with rectangular coordinates negative 1, 1. We see this is our ordered pair, x and y. If we take the tangent of theta, we know that it's equal to the quotient y over x, which would be 1 over negative 1 or negative 1. And theta would then be equal to the tangent inverse of negative 1. If you perform that on your calculator, you'll get a value of negative 45 degrees. Now let's examine this for a second. Our point negative 1, 1, if you graphed it, would be in quadrant 2. This angle is in quadrant 4, however. So we'll add 180 degrees to it in order to get us over into quadrant 2, and we see that we then have a value of theta equal to 135 degrees. Now let's find our r value. It's equal to the square root of x squared plus y squared. So we have the square root of -1 squared plus 1 squared, which is simply equal to the square root of 2. So we get 1 point is the square root of 2, 135 degrees. And then another point we could find would be to take 135 degrees and subtract 360 from it. We could have also added, but we'll then get -225 degrees. So that gives us another point. Equations such as r equal 3 sine of theta, r equal 2 plus cosine of theta, or r equal theta are examples of polar equations where r and theta are the variables. The simplest equation for many types of curves turns out to be a polar equation. To graph, we evaluate r in terms of theta until a pattern appears. One technology note: when graphing in polar coordinates, make sure the calculator is in polar mode. So let me show you how we can do that. On our calculator, we press mode and arrow down to where it says function and arrow over to POL and hit enter. And now we've converted to polar mode. We want to find the polar equation of the line ax plus by equals c, knowing that x is equal to r cosine of theta and y is equal to r sine of theta. We'll replace those with these values in our equation here. So we have a times r cosine of theta plus b times r sine of theta equals c. So here we can factor out an r out of both, and we'll get a cosine of theta plus b sine of theta is equal to c. And now let's solve for r by dividing by our value here. And we see that we get that r is equal to c over a cosine of theta plus b sine of theta. And this is our polar equation of a line. Now let's look at the equation of a circle. X squared plus y squared equals a squared. Remember that r squared is equal to x squared plus y squared. So we have, if we replace our left-hand side, we have that r squared is equal to a squared. We take the square root of both sides, so we'll get that r is equal to plus or minus a. And this is the polar equation of a circle. Notice that r can be negative in polar coordinates. Let's look at graphing a polar equation. To graph r equals 1 plus cosine of theta, we see here a table listed, and I'll show you how we can create that in our calculator to give us some ordered pairs, and here we see our graph. When we try to do this on our calculator, the first thing to do is to make sure you're in polar mode, which we already have, and when we press y equals, you'll see that we have r equals instead. So we'll type 1 plus cosine and use your variable key. Notice that theta is your third option here, and theta will pop up. Now we want to go into our window, so we press second window, go into our table setup, is second window, and we'll have our table start at 0 as it does here, and we want to have our table change by 15 and make sure that it's on auto, and we'll press second and graph now to see our table. And you should see that these values are matching up, and also make sure you're in degree mode. If not, this will kind of cause a problem. And you should see that these are matching up exactly the same as we have in our table here. Now we can graph. The best window to graph is the decimal window, so we'll do zoom 4. And be patient when you're graphing. This can take some time. This particular graph is what we call a cardioid. Sort of looking like a heart. Now if our window had been a little bit different, we would have seen our curves here a little bit better. On our graphing calculator, we could change the window to the following in order to see our graph a little more clearer, and this is what we would see if we changed it. So notice you can see the curves much better with these window settings instead of the zoom 4. But either one will work, so I'll write that out here so that you have it. Zoom 4 works as well. You just notice that it wasn't quite as good of a zoom. In this example, we want to graph that r squared is equal to cosine of 2 theta. So on your calculator, basically what you'll have to do is graph r1 is equal to the square root of the cosine of 2 theta, and r2 is equal to the negative square root of the cosine of 2 theta in order to get both sides of our graph, the plus or minus. So let's pull up our calculator, and what I'll do is we'll convert our window to the specifications I've laid out previously. We'll change our step to 5. We'll change x min to negative 2.35 and x max to positive 2.35. We'll change our scale to 1, or leave it at 1. We'll change y min to negative 1.55 and arrow down, and we'll make y max into positive 1.55 and leave our y scale at 1. And now let's go to y equals and graph the square root of the cosine of 2 theta and then the negative square root of the cosine of 2 theta. We hit graph. You'll see that we get the same picture, and this is what we call a lemniscate. Kind of looks like an infinity symbol. Here are the different ways we can classify polar equations. We have circles, which are clear, lemniscates, which look like 8s, basically, limacons, which sort of look like lima beans, if you look at them, and then rose curves, which looks like different kinds of flowers. Now let's look at converting a polar equation to a rectangular one. In this example, we're given the polar equation r equals 4 over 1 plus sine of theta, and we want to convert to a rectangular equation. So we take our equation and we multiply both sides by our denominator, so we end up with r plus r sine of theta equals 4. Remember that r is equal to the square root of x squared plus y squared, and y is equal to r sine of theta. So here we have the square root of x squared plus y squared plus y for r sine of theta equals 4. And we'll solve this for our square root, so I'll subtract y. We have the square root of x squared plus y squared equals 4 minus y. And we'll square both sides, so we get x squared plus y squared equals, and when we square this, we'll end up with 16 minus 8y plus y squared. We'll subtract y squared from both sides to solve for x squared here. And we get x squared is equal to 16 minus 8y, or x squared is equal to 8 times 2 minus y when we factor out an 8. And this is our rectangular equation. Now we want to use a graphing calculator to graph the polar equation for theta between 0 and 2 pi. Here in this figure we see it graphed. If we pull up our calculator, we'll type in 4 divided by 1 plus the sine of theta, and we want to do zoom 6 to get the window they've indicated here. And notice that we have the same graph. Now let's graph the rectangular equation. So remember that our rectangular equation, we had x squared was equal to 16 minus 8y. So when we solve this, we'll get that negative 8y is equal to x squared minus 16, or that y is equal to negative 1/8 x squared plus 2. So let's change here, and we need to change our mode back to function and go to y equals and type in our negative 1/8 x squared plus 2, and we graph that in the same window, and we see that it's identical. Now let's look at converting a rectangular equation to a polar equation. For the rectangular equation, 3x plus 2y equals 4, first we want to convert to a polar equation, and then we will graph our rectangular and polar equations. So here we'll let x equal r cosine of theta and y equal r sine of theta to get 3 times r cosine of theta plus 2 times r sine of theta equals 4. We'll factor out an r. We get 3 cosine of theta plus 2 sine of theta equals 4. Or r is equal to 4 divided by 3 cosine of theta plus 2 sine of theta. In part B, we want to graph our rectangular equation. So we had 3x plus 2y was equal to 4, and we'll solve it for y. So 2y is equal to 4 minus 3x, and then y would be equal to 4 minus 3x divided by 2, or y is equal to 2 minus 3/2 x. So again, we're still in our function mode, so we'll graph 2 minus 3/2 x, and we see that we have our line graphed as so. And now we want to verify that when we graph our polar equation, it's identical. So let's go pull up our calculator. We'll press mode and convert to polar mode. Clear our screen, press y equals, and we want to do 4 divided by 3 cosine of theta plus 2 sine of theta, and hit graph. And here we see we have the same equation graphed.